stream.
I just remembered the link, so I just clicked on.
Okay, you can see it from so I'm logged in. Let's see if anyone else is logged in.
Why does it say that it's offline?
Because it's just takes a while. Now you can type a note over there saying we're having some camera issues with the video piece. Ask if anyone is watching. The camera's not working, but we're on. So how do you go and we'll try and troubleshoot? What?
Yeah,
It's not working, but how about you go on and then it's not clear if anyone is watching right now today.
Okay, that's fine.
Zero watching now. It says nobody's watching.
Yeah. Okay.
Is it?
All right. Welcome to CS6150. This is Advanced Algorithms. Let's see. So we got a bit late getting things set up, but hopefully we're on track now, or will be. My name is Suresh Venkatesubramanian. By the end of this course, you may not know much else, but you will be able to pronounce my name. I see many of you here. Quite a few of you who were here last year. I'm glad you liked the course so much you took it again. Well, I will warn you though, and we'll get to this, that this course will be a little bit different from what you saw last time, which might be a good thing or a bad thing. We'll see. So, some administrivia first. There is a course webpage on Canvas. I'm sure all of you know how to use it. I would show you right now, except my internet is not working. But just if you go to the Canvas page, you should be able to see the syllabus there. It's fairly detailed. I'll talk a bit about it right now. The first thing I would like you to do, first assignment I have for you on day one is a quiz. It's a very simple quiz. There's no wrong answers, and I won't even know who answered what. But I would like you to check one of the choices to let me know why you're taking this class. I have a bunch of choices there based on what I have gleaned from past years. And if that choice doesn't appeal to you, there is another option, or you could just post a comment. It won't be 100%, or you can email me. Just curious to know the different reasons people have for taking this class. Having said that, I have been asked to remind you all by our Director of Grad Studies, Neha Kasera, whom you've probably heard before, that because of a change in requirements, if you are in the computer science program, not one of the computing tracks, but in the main computer science track, this is now the theory requirement. It used to be the case that it was either algorithms or 6100 logic and automata. That has been changed. So this class is now the required class. It will be offered 3 times, not just once a year. Thanks, Jeff. And everyone, Jeff Phillips, for taking care of all this and getting this working. Thank you. This class will be offered 3 times in the next 4 semesters. So, if for whatever reason you have constraints, you're unable to take it this time, that's fine, don't worry. Even though it is a required class, there will be other opportunities for you to take it. Okay? Including next fall and possibly next fall 2016 and possibly spring 2017. Okay. Yes. All right. So please do take the quiz. I'd like to know again your reasons for being in this class. It doesn't. Again, it helps me to get a sense of where people are coming from. All right. Because this is a relatively large class, we have a lot of students. What I would like for as much as possible is if you can use the discussion forums for your question. And of course, there are multiple reasons for this. First reason is if you email me or the TAs, we're going to get drowned in a bunch of email. And there's a very good chance, probability no less than 1/3, that I will not see your email. As we do randomized algorithms, you'll see why it's 1/3. So, if you do post the discussion forum though, not only will you get an answer to your question, 10 of your friends will also get an answer to their question that they were too afraid to ask and were afraid if they asked they would look silly asking it. So if you can be the brave one to ask that question, you realize that everyone else will want to know the same answer as well. And trust me, this happens all the time. Even though you think, no, this is the one time you're asking a dumb question, that no, everyone has the same questions. The discussion forum gives you a permanent record, people can go back and search it. It just makes it easier. So I will be, so if I ask you to be on the discussion forum, I promise I will also be there fairly actively, and I will make sure to try and answer questions. I won't promise you 20 minutes or your money back guarantee, but I will try to answer them as quickly as I can. So please do use the discussion forums. We're still working out the details of the TA office hours. We do have 3 TAs, but I have to sort of work out something. By Thursday, I will give you the names and their office hours and where you can contact them and why you should not hound them at 3 in the morning, even though some of you may be tempted to, and things like that. Okay, so that's pretty much it as far as the basics of the course goes. And again, if you now, coming to the course mechanics, as you may have known from past iterations, there are no exams in this class. But there are homeworks, and there is a project. Their breakdown, and again, all of this is the syllabus, you have to write this down. It'll be 75% for the homeworks, 25% for the project. The homeworks will be a certain number. Again, I'll say more about this on Thursday. I'm still working out the details of some of these things. The project will be basically a group of 2, no more than 2, possibly 1, but I suggest you use 2, where the goal will be to read a paper and write a report. How hard can that be? It actually can be quite hard. So, and I have a fairly detailed project page explained, where I explain what needs to happen. I would encourage you to go look at that page on Canvas and read all the expectations. I will say more about this in the days to come. For today, you don't have to worry too much about this, but soon-ish, I will be expecting you to start looking at papers and trying to figure out something you might want to read up and understand thoroughly and write a report on. So that's the other thing. So that's 75-25. That's pretty much all you're going to have for the semester. Before I go on to tell you more about the course, do you have any questions about the mechanics? So one last thing I want to mention, some of you are signed up as data certificate students. You probably use section 2 to sign up. You will be very puzzled because that page for your class does not exist. This is because I have asked Canvas to merge the 2 sections and they haven't yet done it. When it happens, and I hope it will happen soon, you will see the same thing that all the other 100-odd students are seeing. So don't worry if you can't see anything right now. It'll all get fixed. Okay? All right. Are there any questions before I go on? No? Good. Excellent. So, what is this course about? Well, it's about algorithms, and allegedly more advanced algorithms. That's what the name says anyway. What do you think that means? So I will be asking people questions a lot, so I like to get a bit of interaction in a large class like this, so this is my first question. What do you think algorithms is? Someone from this side. Put up your hand and introduce yourself, and maybe one day I'll even remember your names. Anyone? This is a course about algorithms. What do you think it is? There's no wrong answer to this question. There may be answers that make me cringe, but there's no wrong answers. Anyone from this side? Put up your hand and introduce yourself.
I would say that it means a series of steps to accomplish a certain task.
It's a series of steps to accomplish a certain task. That's an algorithm. Matt.
Yes.
Matt, yeah. Good, thank you, Matt. Okay, what do we study when we study algorithms then? Someone from that point. If we're studying algorithms, studying a set of steps to perform now seems horribly boring. So hopefully we're studying something more interesting than that. So what are we studying when we're studying algorithms? Yes. Your name?
Zach.
Zach.
My understanding is the most efficient way to solve the problem.
The most efficient way to solve. If I can ask you a follow-up, what does that mean, most efficient?
Usually less time.
Usually less time. You say usually, do you mean there are other ways?
If there are, I don't know, but I just threw in usually as the safety.
As a safety. We have a hedger here. Just in case. I saw a hand up at the back there. Your name?
Jared.
Jared. Sorry, is it Jared?
Yes.
Okay.
Usually time, maybe memory.
Memory. Okay, so space. Anything else? Yes?
Maybe easier, the easiest way.
Easiest way. Your name?
Ideal.
Hadi. So what do you mean by easiest? How would you measure easiest?
Not complicated.
Not complicated. Okay, good, very good. Not complicated. Good. Another thought? Your name?
Correctness.
Sorry?
Correctness.
Correctness. Your name?
Follow.
Sorry.
Follow.
Correctness. That's an interesting one. For the most part, try to make sure they are in fact correct. We tend to view correctness as either it is or it isn't. That sometimes is less true than we would like, but generally yes. Correctness is the thing we start with. It has to at least be correct. For a lot of heuristics, which I will distinguish from algorithms, even that's not always clear, whether they're correct or not, but they seem to work on some inputs, so we're happy. But that's a good point, that we want to make sure they're at the very least correct before we start worrying about efficiency and all things. Thank you. Okay, good. So these are all very good, but it's a sequence of steps that performs a certain action. We want to make sure we want to design a sequence of steps that performs an action in the least amount of time or space or complexity or simplicity of some, or most simplicity, and we always want it to be correct. This is a pretty good working definition of an algorithm. And while we could, look at any given problem and say, okay, how do we solve this and think very hard about it, that's just too much work. And the whole point of algorithms is to be lazy as possible. Let something else do the work for us. And so what we want are weapons at our disposal that will allow us to solve large classes of problems with one shkum, right? So the goal of studying algorithms is not just to study this one or that one or the other one. We want to study tools. We want to build up a toolkit that we can use to attack many different problems. Because when you're out there, for many of you, this will be the last algorithms class you take, and you'll be working in some other area, and you'll have some problem there, and you want to solve it. What you hope to get out of this class, what I hope to give you out of this class, is a bunch of weapons. You don't know which of them is going to work. You don't know if your problem is, a screw or a nail or something else, but you can try. You can try all these different tools, and hopefully one of them will get you somewhere. And if they don't, it'll get you part of the way, and you can try something else, it'll get you part of the way, and so on. So studying algorithms is fundamentally about studying tools, right? And so since no single weapon can beat all enemies, you want to have a bunch of weapons so that you can, account for any possible eventuality. And of course, that will never happen. There will always be a new thing that we don't have a solution for, and that's why I have job security, or at least I think I do. So, all right. So, in an undergraduate algorithms class, and I'm going to distinguish what we're going to be covering here from that. You hopefully have studied, or at least have some familiarity, or some vague thought in the back of your long-term memory about things like, let's see. We'll have to learn to write larger. Okay. So the first thing you might learn are things like recurrences, right? Things like, oh, here's an equation. You must solve this equation. How many of you have seen something like this? Good, good. This is a recurrence equation. The point of this equation is it's usually characterizing something like the running time of an algorithm. The running time of an algorithm is T of n. We can express it recursively in this form, find the running time. So you study things like recurrences, basic mathematical analysis. And so you study recursive algorithms, and the most easy recursive algorithm to study is something called a divide and conquer. Okay, so from the middle three rows, someone, give me an example of a divide and conquer algorithm. Anything you want. Sorry, Danny? Yeah?
Merge sort.
Merge sort. And who will? Yes. And what is your name?
Shweta.
Shweta. So three of you said merge sort. So we'll write on merge sort. It's a divide and conquer algorithm. Why? Because the whole point is to divide the problem into smaller pieces and then merge them together. In fact, a divide and conquer algorithm is really cool because you just keep dividing. All you have to do is figure out how to merge them. And then the recursion fairy takes care of everything else. Everything just comes up. And then you get recurrences. Okay. You have probably heard of another kind of recursive algorithm called dynamic programming. The most badly named algorithmic design paradigm of all time. It is, yes, there is a program involved, but it's not very dynamic. So. In fact, it's very hard to use dynamic. Anyway. Example of dynamic, next three rows, someone. Dynamic programming. Give me an example. Any example of a problem whose quintessential solution comes by using dynamic programming. Next three rows. You're only in the first three rows. Next three rows. Yes?
0-1 backpacking.
Sorry?
The backpacking, the 0-1 backpacking.
0-1 backpacking.
Like you can either take you have a bunch of things that each has a weight. So you need to put as many stuff as you can into your backpack.
Right. Okay, so another name for this is the knapsack problem. But what's the same? So some of you may have heard this under the name of knapsack, but that's the same problem. But in fact, I'm surprised you said 0-1 because that one is actually not, well, you can solve it, but we'll give it to you. It's fine, knapsack. I don't want to get too technical right now, but I will later on. Anything else? From the, yes, back there.
The images, isn't seam carving dynamic programming process?
Seam carving. I don't know. I've never heard of seam carving. What is seam carving?
Try and find, you might have taken the image, say by 1 pixel.
Yeah.
Try and find the path through an image, so you must increase it.
Oh, so you find it like a shortest path or some kind?
Least weight path.
A least weight path.
Find
Okay,
difference.
that seems likely to be dynamic programming. So I'll put a little question mark. Yeah, but I think it is. Okay, good. You have also covered, you know, I call this the Coke of algorithms. Everyone loves to drink it, but using too much of it is not good for you. Greedy algorithms. If you're wondering, divide and conquer is like milk. It's like the basic thing you learn. Dynamic programming is like a spinach smoothie. It tastes horrible, but it's good for you. Okay, from way back in the back, last 3 rows. Anyone would like to name something that, you know, the quintessential solution is a greedy algorithm? Back, yeah.
Job sharing?
What kind of jobs? Not all flavors. There are some flavors that are greedy, some flavors that are not. In fact, there are some flavors that end up being dynamic programming. I think it's unweighted job scheduling. All jobs of equal weight, right? Or something like that. Or at least one version of that. Your name?
Sahana.
Okay, so some variant. Good. So these are some things you probably have covered in undergrad algorithms class, and at least in past incarnations of this class, these are things we would spend a fair amount of time covering now. You've also, the other thing that you've, let me get to that, okay. So, and the way we've studied these algorithms, or these algorithm design paradigms, is by the way, I will put up all these notes somewhere where you can look at them, so don't worry too much about right now. You study them by applying them in specific contexts, right? So you have a tool, okay, so I have a tool, that's fine, but I have to apply it to a problem. And some of the typical domains where you might have applied these solutions, these algorithm design primitives, are things like, I don't know, dealing with strings, right? So you want to find a longest common subsequence between 2 strings. So there's a dynamic programming solution for doing that. You might have tried to find the minimum span, and so then again you have a greedy algorithm for doing that, right? You might have even looked at some kind of number problem. So the example of the knapsack problem is basically a kind of a number problem. You have a bunch of numbers and you want to organize them in some way. You might even have looked at some geometry problems. You have points and lines and you have to do something there. And so, I mean, in particular, we're not, of course, you know, these are abstract domains, and I'm not saying that we necessarily care about strings and graphs and numbers and geometry. Well, I care about geometry, but you may not. But these abstractions, these are all abstractions of real world problems, right? And the key, if you say that, you know, what is it that computer science has offered the world, right? It's offered a couple of things, but among them are algorithms and abstractions. The idea that you can take a problem that looks very messy, pull out what appears to be the core underlying computational question inside there, and then solve it. So we want to do, you know, so we want to do something with Facebook. We want to capture some notion of a social network. What do we say? Oh, well, let's think of it as a graph. It's a very innocuous thing you do when you say that. You almost don't think about it. But if you haven't been trained in computer science, this is not something that comes naturally. To say, oh, let's think of it as a graph. People say, well, what about this? What about that? You worry about these cases. The key to computer science and to algorithms is to understanding when you're given a new problem, what kind of formal structure is underlying it, and then what kind of problems can you apply. So people will often say to me, oh, so you work in data, what kind of data do you mine? I'm like, well, it doesn't quite work that way, because what I do is I look at general abstractions of data, points, lines, graphs, whatever, and I come up with solutions that work across these abstractions. Now, whatever your actual problem is, you can put it in one of these abstractions, because over the years we've learned that these are good abstractions to have, and now we study them. Okay? And things change over time. Before, the motivation for studying graphs used to be finding shortest paths. You want to go from A to B, and you want to find a shortest path through it. Nowadays, it's all about the social networks and the community structure and this and that, and so things change, but the abstractions don't. And sometimes we come up with new abstractions that weren't necessarily interesting before, and that's what makes all of this very interesting. So this step process where we say take a problem, a real-world problem, abstract it in some interesting way, and then apply our tools to it, is the essence, the core of how we think about things in computer science and how we think about things in algorithms. And again, at the end of this class, while you may not remember all the things I tell you, you may not remember all the details, all the analyses, that's fine. What should hopefully go away with is a way to learn how to abstract problems and how to attack them with some of the tools we will learn in this class. And that's the goal here. And this brings me to the next thing that I think is very important and is maybe not as emphasized as is the idea of an abstraction. One of the things I missed out in the topics you cover in any kind of undergrad algorithms class is NP hardness. Maybe you blocked it in memory because it was so traumatic. That's also possible. So, but NP hardness and the idea of complexity theory is a completely different, or not different, another layer of perspective on the study of algorithms. So I said that algorithms was the study of tools, of weapons, things to attack problems with. But it's also the study of problems themselves. Okay? And complexity theory, of which we'll talk a little bit in this class, is about trying to say all of these problems are essentially the same. They're all equally hard or equally difficult. I can either apply the same weapon to solve all of them, or I know that none of my weapons will solve any of them. The ability to say this is the essence of complexity theory. So complexity theory and if you're a physicist, you will know that you guys have stolen the words from us, and I'm not very happy about that. It does not mean what it might mean in physics. Complexity theory in physics means something, frankly, I have no idea what it means. But in computer science, I know exactly what it means. Are there any people from physics here? No, you're not going to raise your hand, because now you're too scared. Okay, fine, well, I won't do anything. Any physicists? Any people in physics training? One? Ah, there you go, see? And this is again, a very important part of studying algorithms. Even if you never do complexity theory, the reason why you want to appreciate that we group problems together is because, again, we want to be lazy. If I know I can solve this problem, and this problem is like that problem, yay, I don't have to solve this problem, I just use this one. Right? The idea of a reduction. You use this all the time when you write code. But you can elevate this to a much more formal reasoning about these things. And it's all about names. So I don't know, I mean, throughout history, you can go back to ancient times, the idea has always been that names give us power. If you name something, it has power. If you know the name of something, you have control over it. If you read Rumpelstiltskin, that's the whole point of the story. Names have power. And in the same way, if you go through a baptism, then that's when you're given your real name, and that's a great moment when you're actually given a name. The same way, when we give a problem a name, we give ourselves power to understand that problem. And this is something that we do unconsciously when we study algorithms. That is not surprisingly as common outside the field, and something that I hope that you take back to wherever you're coming from. That problems have names. They have a character of their own. And it's important to recognize the difference between a problem and a solution. When we name problems, we can go looking around for them and get information about them. If I say, oh, this problem we're looking at looks like vertex cover, I have now named it. And now I can go attack it a certain set of ways. If I say, no, this problem looks like a traveling salesman problem, I have named it differently. And now there's a whole other set of things I can apply to it. So being able to name a problem is sometimes the first step to figuring out which tools to use, right? If I don't know there's a difference between something called a screw and something called a nail, I won't know that one needs a hammer and one needs a screwdriver. And that naming process again seems incidental and innocuous, but it's a very, very important step in knowing how to apply algorithms. And so that's one thing we'll also talk about. I'll try to emphasize that. We talk about names, we talk about problems, we talk about classes of problems. We talk about things you can say about entire classes of problems, entire classes of solutions. And this is a very powerful thing. Okay. So, more details. Some of you have, again, seen this class before. You've talked to your friends. You may have even sat through this class before. It had a certain set of topics in it. This class will not. It overlaps, but not as much as you might think. So let me try to explain the landscape of what we did what we did before, and what we're going to be doing this time. And again, this is all in the syllabus. So let's say, 2014, 2015. Okay. So what were we covering? We actually spent some time covering recurrences, the master theorem, and things beyond, divide and conquer, dynamic programming. We covered greedy algorithms. We covered flows, max flows, NP hardness. Let's see, we did some randomization. We did some approximation. Chitruli, where are you? Have I missed anything? What else did we cover? That's pretty much it, right? Yeah. Okay. So, what are we covering this time? We are covering all the stuff at the end of the previous class, actually. We're covering randomization. We're covering approximation algorithms. We're covering linear programs, and again, all this is going to be in the syllabus. LPs, flows, duality, and good stuff like that. We're going to be covering advanced optimization. So things like semi-definite programming and multiplicative weight updates, or boosting, or what you may call boosting in the machine learning literature. We'll be covering some high-dimensional thinking, how to think in dimensions more than 2 or 3 or 4, how to think in infinite dimensions. That can be quite pleasant in the brain, or a little insanity-conserving hokey. And a bit of learning theory. A teeny bit, just for fun. So we're not covering, basically, stuff that here is all this. This is gone. So why am I doing this? The stuff that I've just mentioned there, that I'm actually crossing out, is really part of an undergrad algorithms class. The reason I've been spending a lot of time covering it in this class in the past has been, in some way, as a kind of refresher. And over the years, I've actually shrunk the amount of time I spent on it. The main reason is that it's very easy to spend an entire class, in fact, there's an entire undergrad class, on those topics. And all of that is stuff that was basically, I don't know, invented in the 70s and 80s. And as a history lesson, while it's fine, the world has become a lot more interesting and exciting place with all the new things we've learned in algorithms in the past, I don't know, 20, 25 years. And especially in this sort of so-called big data world. You have to put scare quotes whenever I say big data, because there's no other way to say it. Big data. There are tools that we use that are way more important and way more useful and way more practical, in fact, than knowing the core material, which you should be knowing already. Some of these tools involve how to do things in a randomized way. It turns out, for example, that for many problems, there is no way to solve them with an algorithm that just is a fixed sequence of instructions. You have to allow the algorithm to go to Vegas and spend some time. And that's what these things do. There are many problems for which you cannot get an exact answer. You can provably not get an exact answer. So either you can just give up and throw your hands up, or you can say, well, can I get close? And can I get close in a provable way? That's the key here. I'm not just going to hand wave and say, well, I think I'm close. I'm going to actually prove it to you. That's where you get to approximations. Since we want to study not just single tools, but classes of tools, the idea of linearity, linear programming, is extremely important because many problems suddenly reveal all their secrets once you look at them through the lens of linear programming. And otherwise they seem very weird and artificial. So having that lens in your mind is very important. I've talked about this in previous incarnations of the class, but I'm going to spend a bit more time on it. And this will lead me to things like max flows and matchings and other things which are very important tools. These advanced optimizations, they seem exotic, but they're actually very simple once you have this layer of understanding about basic optimization. And they're again very, very important in the world we live in today, with matrices and spectral methods and graph analysis and things like that. I mean, it should be clear that a lot of the data we live with is high dimensional. It has many, many features, and you have to learn how to live with that. And the way to think about these kinds of problems, again, how do you change the way you think is very important. So I'll spend some time on that. And because a lot of you are in the data program, I think it's important to understand the connection between core algorithms and machine learning. So I'll spend a little bit of time on learning theory. Many of you are in Vivek Shivkumar's machine learning class, and you'll cover much more in there as well. I will mention that we have another faculty coming in. He'll be joining in January. His name is Aditya Bhaskar, and he does theory. He also does theory of machine learning. And if you've taken this class, you'll be well prepared, and I've talked to him about this. You'll be well prepared to take his class next, which covers more advanced material like spectral methods, random walks, Markov chains, and other fun stuff that you will often come across. Okay, so I will say more. Some of you, if you come for the research buffet on Wednesday, I'll talk a little bit about his work as well. So something to keep in mind. Okay, let's take a 5-minute break.
Yesterday's training, I see you take a lot of time.
Not really, actually. The camera was just not working initially.
Okay, you fixed it. Because I know Jeff mentioned yesterday.
Yeah, we had those icons coming up, so I just removed them. I'll tell you, I think I have an email. I'll just forward it to you. Just sent to me sometime before.
Is it recording right now?
Yeah, it is regarding how to remove the icons from the
But our voice will okay.
So we are taking this course?
Huh?
We are taking this?
Yeah. I didn't get the chance to register last year because class is full. But the topics all change. Two different courses.
Oh, that's
the rest of the lecture for today. Are there any questions about the class so far? Yes,
These
Mike.
will be published to online.
Pardon me?
Your lecture.
I will. My horribly written scrolls will be published online. Yes.
Awesome.
Yes. No, not the. Yes, Daniel.
When will the homeworks be available?
Yes. Thursday. Thursday I will have more information about the homeworks. Sorry. I'm getting into the swing of things. So, yes. Other questions? Yes.
So the topics that we won't be covering in this class,
Sorry?
so the topics that we won't be covering in this class, are there like brief notes from the last class that we can refer to?
Yes, and I will actually put that online on Canvas for you to review. For the most part, for those of you who are familiar with this, I'll be using Jeff Erickson's lecture notes, which are free and wonderful and have lots of jokes and are available online, most importantly. So I will be using that for review. I will also be giving out assignments with sort of memory tickling questions to make sure you remember some of the stuff in there. So that'll be part of the homework suite. There'll be some refresher of the stuff that you hopefully will remember from before. Other questions? Okay. So we're going to start today with the idea of randomization or a randomized algorithm. Let me first tell you what it is not, because that often causes a lot of confusion. What a randomized algorithm is not a randomized algorithm, in the sense that I will be referring to it, is not a regular algorithm with data drawn from some probability distribution. That is often what people think a randomized algorithm is. What it is you laugh. It's a serious problem. A randomized algorithm is an algorithm that, in addition to all the other normal steps it might take, is allowed one extra step where it takes its lucky coin out, tosses it, and goes one way if it's heads and the other way if it's tails. That's it. Okay? Which means that if you run a randomized algorithm 2 times, you might get a different answer both times. Based on the coin tosses. My son has just started learning Dungeons and Dragons, and as you all know, as those of you who know Dungeons and Dragons, there's a lot of nice randomization in there, just like life. So, the reason we study randomized algorithms is because it turns out that for many problems, that can be defeated by an adversary. So I will often refer to an algorithm as playing some kind of game against an adversary. The reason I will do that is because when we want to say that an algorithm always does something correctly, what we like to imagine is some kind of adversary who's trying to make the algorithm fail. And the algorithm blocks and parries and resists everything the adversary can do. Some problems cannot be resisted. The adversary is too strong, it turns out. We don't know this for sure, but we believe that there are problems for which, at least we have examples of problems for which it seems hard to resist an adversary if you can't toss coins. But if the algorithm is allowed to toss coins, it can suddenly go whoop, and then suddenly miss a blow, and essentially be able to solve the problem. We'll see how this works out. And the problem we're going to be looking at in order to study randomization is a problem that you all are probably extremely familiar with and have used over and over again. We are going to use the problem of hashing. How many of you have invoked a hash function at some point in time in your code? Yes, you all have. So you all know that hashing is something that's very, very useful. Or many of you have. What we're going to try and understand today, and hashing is one of these very, very clean examples of where I can guarantee you that a deterministic solution, a deterministic is something that's not randomized, a deterministic solution will not work, and a randomized solution will work. It's one of these clear bifurcating problems where you can see the difference, and that's why I want to show it to you. Okay. So what is the problem of hashing? So let's be specific. In hashing, the goal is the following. I have some collection of items drawn from a universe, and I want to store them in a table of some kind. Okay, I don't care what this looks like, I'm just drawing it like a table, but it's some kind of data structure. And what I want to do, and I'm going to put a little bar here because I have an API attached to it, and all I want to do is ask this data structure, is an element in the set or not? Right? So again, I want some kind of abstract data structure that can store a collection of elements, and now for any other element can ask me, is it in the set or not? Right? Okay. So to be more precise, we'll assume that we have some universe. We'll call it U, where all the elements are drawn from. We'll assume we have some set that we want to hash. S. And we'll say that the universe size is equal to U, and the set size is equal to N. We will assume that U is much bigger than N. That's where hashing becomes an interesting question. So what do? I don't want the correct answer here. I want things you might try. So again, in all of the stuff we'll do in this class, it is the journey to the answer that is way more important than the answer itself. And all the blind alleys we go along, all the things we get wrong. That's where you learn. The answer itself is a little, certificate at the end of the problem journey, but the journey is far more interesting. So,
I have a question.
Your question. Your name is? Praful, yes.
Is there a distribution of the question being asked, like what elements are more likely to be asked and what are?
In this setting, no.
No.
No. There are potentially settings where you might want to ask it that way because you might have some prior information about your data. We're not considering that here. And that's why I emphasize that when we think about randomization, we are assuming arbitrary inputs. Not random inputs, but arbitrary inputs. Yeah, good question. Yes?
Can you just repeat the question itself one more time?
The question is, how do I build a data structure that allows me to answer membership queries, is X in S, when I'm given an arbitrary set of elements of size N drawn from a universe of size U, which is very big. Your name?
William.
William. That's the question. Thoughts? Anyone? Yes?
I guess if the elements have order, then you can just sort it and using binary search.
You can.
Or
Absolutely.
you can create a binary search tree in a sense.
Absolutely. So you can create a binary search tree. So let's write that down as an answer. So you could create a binary search tree For those, who all are familiar here with the binary search tree? I shouldn't ask questions like this because there are enough hands that I can't tell the people who aren't putting up their hands. So this is some number more than 50% know what a binary search tree is. That's all I can tell from this. So a binary search tree is basically a tree where if the elements have order, as you correctly point out, you can put them in a kind of less than or greater than or equal to order here. And you can put them down here. You can, maybe it looks like this. And you can even balance the tree if you're very clever. You can use some kind of red-black trees or AVL trees or some other some kind of mojo. And make sure that you can, for any query, you can now say, okay, let me go down this thing and let me see, and if it's there or not. How long does it take to do a query in such a structure? Since you mentioned the binary search trees.
Log n, but if it's not balanced, then it could degrade to n.
That's right. So it takes log n if your tree is nicely compact, because a binary tree has log n depth if you have to. But if it's not, if you have a long stringy tree, it might be worse. Let's assume we balance it. So let's say it takes log n time to do a query. Your name?
Joe.
Okay. So we've solved our problem. We have, how much space does this data structure use, just out of curiosity? How much space does this data structure use?
Is n.
It's n space. It's great. So we have our first solution to our problem. So our first solution has, so I'll say BSTs. We have n. And the query time is log n. Yes?
So we're assuming in this case that the members of the universe have a measure of some kind? Like a measure?
They have an order,
Order, okay.
not a measure.
Are there any other properties we're assuming of this universe?
That's a very good question. All I know is that they must have order, and you must have a very efficient way of determining that order.
Okay.
So if they were ordered, but it's an NP-hard problem to figure out which one is more than the other, then this would not be log n time. More precisely, it's log n invocations of your comparator function, whatever it happens to be. So we'll assume that you have an efficient ordering function that can tell you which one is bigger than the other. Good. So we'll assume, put here, ordered universe. Now, the ordered universe restriction is not a terribly bad restriction. Suppose I had data that wasn't ordered. Can someone name, let's see, it's from the back 4 rows there. Can someone name a kind of data that is not ordered naturally? Yeah?
Any sample distribution.
Any? A distribution. So you're comparing two distributions, you're saying? Two probability distributions?
So, like for example, if you take samples of a multi-probability distribution, then there's no way that they can order.
But the samples are in which universe? Pardon me? Okay. So for example, so let me see. So suppose I had points in the plane. Suppose I had points in the plane in 2 dimensions. Can I order them? I could try, but there's no obvious way to order points in the plane. You could order them from left to right, up to down. You could do all kinds of things. But there's always a way to find some ordering. If you've all heard of lexicographic ordering, you just write down some encoding of the object and you treat it like a big string and you order things one. So you can get around the lack of ordering, but it's not, you can do it if you want. But suppose I'm greedy. I want more. You got me n log n, but that's yesterday's news. Today I want constant time access because that's just how I roll. I want constant time access. Now what do you do? Wait. So let me see. There's some section I need to take on. Okay, last 4 rows back there. I want constant time access. What might I do? Yes, Pavel.
Map the elements in U to some number,
Map the elements in U to some number.
which would be the mapping function.
You're getting close to what we need to do in this lecture. But there's something even simpler you can do actually. There's something much simpler that will work. That's good. What you're saying is on the right track, but I want something even simpler. let's see. So, Daniel, right? Yeah.
You can have a data structure as large as n.
As large as n.
Yeah.
Okay.
And then from there, what you can do is just order the elements and keep track of where they are.
Isn't that a binary search tree? I mean, if you say keep track of where they are, how are you going to do that in constant time?
Well, it's going back to that whole number thing.
Ah, okay. There was a back there, right back in the corner.
You'd rather have it the size of u?
I don't care. You can do whatever you want. Just tell me an answer, yeah.
So if you have it the size of u, then since you have some order, you can look exactly where you want it and if it's there or not.
So the solution that I think is being proposed is make some kind of structure of the size of u. Yes? And then what?
And then basically you can either just keep true or false with everything.
So you put a bit like that. So 1,
Knowing that
1,
they're not.
1, 1. Like that?
Yeah.
Is this constant time query access? To get an answer to whether something is in the array, what do? I just go look. Is it a 1? Yes, it's there. Is it a 0? No, it's not. Okay. So we'll just say, we'll call this the big table solution and hope Google doesn't come and yell at me for this. What's a space required for this? U. Yes, that's right. Good. And does this require ordered universe? Do we require any assumptions on the input? No. It's all good. Okay, we're done with hashing.
Well, what required is that we're able to know where to look up in a table. So that in itself requires order, right? Doesn't need.
But it doesn't. But you can put any ordering on the data, as long as you can construct a canonical. What you need is the ability to construct a number from an input. As long as I can construct a number from my input, saying this item is number 537, then I can go with it. But you're right. I need the ability to construct a numbering, which is a weaker thing than constructing an ordering. Okay, good. So are we done with hashing? We have two solutions and both look pretty decent. One has good query time, one has pretty good space. But of course we're not done. We want both at the same time because we're even greedier. What I want is something that is this and that. And that's where things get interesting. Because the problem now is that this can't be done. Not with the deterministic method. If I want always have space, always have constant lookup, it turns out I can't do this. So let's think about this for a second. What we could try to do was use a small table. We say, well, we'll use this big table trick of having bit vectors, but we'll only have a table of size n. So what we're going to do is, essentially what we're saying is that we want some table. We're going to construct some table. In fact, let's say the problem is the following, that we have some table of size. We'll give it a different letter just to make things clear. Okay? Size n. And so we want to store all our inputs in that table. Right? So we want some kind of mapping which will map all our inputs. And this is the numbering thing that we mentioned. Right? We want some mapping that gets all our things to that table. And the problem is the following. How many of you have heard of the pigeonhole principle? Some of you have because you've been in my classes before. For those of you who haven't, the pigeonhole principle is one of the sort of most important, how shall I say, ornithological principles in mathematics, which says that if you have 10 pigeons and 9 pigeonholes, someone's getting a roommate. Or if you have 11 pigeons and 10 holes, someone's getting a roommate, and so on and so forth. This is a very important principle And it's because it applies directly to these kinds of problems, among other things. And it applies in the following sense. Suppose I were to say, I will just pick some small set of size n for some small value n and try to find a function that maps everything down to this set. Okay? So let's imagine that I have some kind of universe. So again, I have my universe U, and I have some set of size n, and I want to map everything down to the set. Right. What the pigeonhole principle says, or what a generalization of the pigeonhole principle says, is that there's going to be some location that has roughly U over m elements mapped to it. There's going to be one crowded house right there. And these are what are called collisions. Okay. Now collisions aren't necessarily a bad thing. In fact, all hash functions will incur some amount of collisions. But this is particularly bad. Can you tell me why this is bad? Can someone tell me why having a hash function that makes lots of things collide in the same cell, even if I have a way of storing them all, is going to be a bad thing? Yes, back there?
There's only one way of having multiple objects.
Pardon me?
There are two elements, there are two objects of the element mapped to a single element of the set.
So why is that a bad thing?
Because you can differentiate between which is what when you do a lookup. Backtracking is not possible.
So there are two problems. There's one way of thinking about this. One problem, what's your name?
My name is Srinivas.
Okay. So one problem is that, as Srinivas says, if you put two elements to one, you won't know later on when you asked, okay, 5 and 3 both went to the same cell, is 3 in the set? I don't know, I just saw 1 there, I can't tell. You could fix that problem. You could say, no. If I have multiple elements showing up in the same cell, I'll put them both in. Now what's the problem? Yeah?
You always have to do comparison.
Sorry?
You always have to do comparison of lookup.
So why is that a bad thing?
Because it costs time.
How much time?
It depends on what you compare.
But it's as much time as the number of collisions. So if you have lots of collisions, you take a long time, which defeats the whole purpose. You can no longer claim you have constant time. So you're stuck either way. If you have a deterministic hash function by the pigeonhole principle, and you don't have as much as the size of the set, you're going to have collisions coming in. Some two elements are going to collide, no matter what mapping you pick. And again, notice what I just said. I said, no matter what hash function you pick, something bad is going to happen. This is a very powerful statement. I don't need to know what your hash function is. But by using the pigeonhole principle, I can reason about any possible hash function. And these are the kinds of powerful statements we'll need to be able to make to reason about these algorithms. I'm not talking about this hash function or that one. I don't care. They're all bad. Okay? That's very important. And so it turns out that the only way to solve this problem. So now let's think about what's going on here. What game is being played? So you're the algorithm. You say, okay, here's my hash function. The adversary looks at your hash function very carefully and says, look, I know the pigeonhole principle is true. If I look very carefully at this function, there's going to be two things that collide. It looks very carefully at this function. It finds two things that collide. It gives you a bunch of those things as the input. Now your analysis is broken because your analysis has to work for all possible inputs. Right? This is how we do worst case analysis. We assume the worst possible input and see what happens. And the adversary got to look at our code, got to look at our algorithm and decide what input to pick. This is a sign. The fact that the adversary had to look at your code very carefully and figure out how to cause a collision is a sign that you need to confuse it somehow by using randomness. Invariably, the place where you apply a randomized strategy is where the deterministic strategy is defeated by an adversary who looks closely at your algorithm and tries to pick some very carefully chosen inputs to beat it. And the idea by randomization is that you can somehow fool the adversary. It won't be able to look because it doesn't know what the algorithm is going to do at any step because the algorithm is going to toss a coin. Until the algorithm actually runs on the particular input, it won't know what it's doing. So there's no way the adversary ahead of time can figure out an input that will defeat it. I mean, it can, but not as well. Okay? So we have the problem, we have a failure, and we have a clue. And that's where we bring out the tool of randomization. And so what we're going to do is, we're not going to assume that the input is well distributed in some way. No. We're going to assume that our hash function is allowed to toss coins. And somehow that will make all the difference. Okay? All right. So what should we do? So what we're going to do is, we're going to pick a hash. So we're going to say pick a hash function from u to m. This notation means this is the set 0, 1 up to m minus 1. Or if you're a hardcore MATLAB person, you can replace it by 1 through m. But you shouldn't be a hardcore MATLAB person, that destroys your brain. So. At random. Okay. Okay. Why is this going to be a good thing? Why this is going to be a good thing is that we will now ask the following question. We have already observed that if we have a hash function and we're trying to put elements into a table, collisions are somehow a bad thing. We'd like to reduce the number of collisions in our elements. We're saying that if we pick a hash function at random, this will somehow miraculously solve all our problems. Well, if it's going to solve all our problems, in particular, it has to make sure, things don't collide. And so the way to ask this question is to say, well, this is a randomized algorithm now. They might collide, they might not collide. The right way to ask the question is, what is the probability that they collide? And in this algorithm, like with all other algorithms we will study in this unit of randomization, when I say what is the probability, I mean with respect to the choices the algorithm makes. So the way to think about this is that the algorithm tosses some coins and gets an answer. And you say, did it collide or not? It collides with a 1, doesn't collide with a 0. Then it runs it again. Say, did it collide or not? Did it collide or not? You tally them all up. And yes, I'm taking the frequentist point of view. If you're Bayesian, don't complain. So this is the frequentist point of view. You tally up all the times when it collided. You look at all the times when it didn't. Fraction is the probability that the elements collide. Remember, this is over the choices the algorithm makes, not over any input. The input is worst case. In fact, it's the same input. Any x and y is equal to 1 over n. Think about it this way. The first element goes anywhere. You don't care where. What is the probability that the second element goes where the first element is? Well, I'm picking my hash functions uniformly at random from all possible hash functions. So the probability of it being in any one of the spots, because it's all possible hash functions, they're all the same. And it could be in this or this or this or this or this. There are n choices of where it can be. There's only one choice where you have a problem. That's one. Right? And I will assert this for now. You can think about this and we'll actually prove this next time. That if in fact the probability of two elements colliding is 1 over n, the expected number of collisions you will see in any one cell is what you'd expect if you put them in as evenly as possible. So in other words, so if you look at the hash table, I'm going to draw the hash table like this, right? And you're going to have some some extra elements here, maybe a few more here, and a few more here. You're going to have some distribution of collisions. What you're going to say is that the expected number of collisions, hopefully you remember what expectation is going to be n over n. Which is again the best possible, right? You have some kind of even, it's as if you throw them in evenly into every cell. In particular, this means that if you choose n to be roughly n, which means some constant times n, then the number of collisions, or the expected number of collisions, is constant. And we now have our solution. Because now we have every item has an expected number of collisions that is constant. That means the table entry has a constant number of things hooked up together. When you have to look and see if your item is in the set, you have to go through this constant number of things. And so you spend constant time to get your answer. And your space is still there. Question?
If your hashing function is a random algorithm, when you go to do your query, how are you certain that it will do the same hash to find it in the right spot?
Aha! We will talk about that next time. To be continued. But that's the basic idea. The rest of the hashing is about how you do that. Yes? Sorry?
When you randomize the hash algorithm, you're only reducing the probabilities of collisions, but you're not making it zero.
Correct.
You are only reducing the number of collisions, right?
But you're reducing the number of collisions to such a low level that it's a constant. You don't have to make I said I want constant time access. When I said 1, I meant O of 1. You want constant access. 3 is okay. 4 is okay. 10 may not be okay, but it's still acceptable within a regime. What I don't want is n, or log n, or something like that.
But is there a solution where you make it zero?
Stay tuned. Yes and no. There's certain things you can do. Yes. Question?
So technically in this case, we're assuming that given a string or an index, if you get to that place immediately, is that a fair assumption? Because it would take on the order of the number of
Bits?
Yeah, representing each one to get to that.
Right. So I'm assuming we can do operations of the order of log u, which is the number of bits required to describe an object, in sort of one operation.
Okay.
So it's a good point. Those operations we will assume are sort of given to us, and so it should be in terms of numbers, O of 1 operations, and O of 1 lookups. Like that. Any other questions? See you all Thursday.